Keep me awake.
All right, and last time we were talking about a free fall problem. Okay, and so we had a ball that was dropped from a height of 1 meter. Okay, and so we had y of t over here. Okay, and we had y equals 1.0. Right, and this was at t equals 0. And then we had y equals 0 down here at t is equal to 0. I believe it was 452 seconds. Okay, and what we said is that y as a function of time, okay, was actually a quadratic equation, right? And so we said that y of t was 1.0. Okay, so y of t, 1.0 minus 4.905 t squared, okay, and that was in meters. Okay, and so we talked about the idea that if I wanted to know the speed at impact, okay, what I really wanted was a derivative, right? And so we talked about the idea of velocity, right, which is at any point in time, the instantaneous velocity, okay, being the derivative dy dt. Okay, and then we introduced what a derivative was all about. Right, the idea that it's the slope of a curve, and we had, graphical interpretation, and we had how do you take derivatives of various functions on here. Okay, and I believe we concluded an answer for the derivative, which we used to get the speed at impact. Right, so what we had was the velocity was the derivative with respect to time, okay, of this function right here, 1.0. minus 4.905 t squared. Okay, and then we recognize that that's actually two different terms. We got the derivative of a constant, and we have the derivative of a quadratic term. Right, and we looked at the sheet and said, hey, we can do those terms one at a time. Right, the derivative of the sum is the sum of the derivatives. Okay, and so we concluded that when I take the derivative of the first term, the derivative of 1.0, a constant, is what? 0. Okay, and the answer we liked was a constant doesn't change. Right, and by definition, right, dy dt is the rate of change of the position with respect to time. So it's 0 here. Okay, and then we had a constant out front, minus 4.905. And we took the derivative of t squared, which gave us what? 2 times t. So 2 times this guy, minus 9.81 t meters per second. Okay? And then in order to find the speed at impact, right, we substituted in what value for time? Right here, right? So the point is, this is the instantaneous velocity, right, at any time. Okay, so this is at any time at all. Okay, so I want to find the speed at impact. I plug in 0.452. If I wanted to find the speed, after a tenth of a second, I could plug that number in as well. All right, so I think this is about where we ran out of time. Okay, and so I want to continue on with some concepts of derivatives, okay, that'll move us into the study of dynamics, which is where we are on the syllabus. Okay, and let's talk about the idea of acceleration. Okay, when we were talking about this thing, a number of people initially said, well, I know it's going to be faster when it hits the ground because it's accelerating. Somebody want to tell me what is acceleration?
Change in speed or velocity?
It's the change in speed?
Or direction.
Change in direction?
Derivative
Derivative of
of velocity.
velocity, right? So it's the rate of change of the velocity, not just the change itself, right? It's the change per unit time. Okay, and if I want to know the acceleration at any specific point in time, I need the instantaneous acceleration. So I want the derivative right, of the velocity. Okay, and so, this guy is rate of change, right? Rate of change of the velocity. Okay, and so in order to do that, then the statement is, just like we had for velocity in terms of position, right? Acceleration is to velocity the same way velocity is to position. So acceleration would be this guy, the limit, right, as delta t approaches 0 of a change in velocity divided by the change in time. Okay, and again, by definition, this is dv dt. Okay, so if I have the velocity v, this is the derivative of v with respect to time. Incidentally, in terms of position, right, then velocity itself is a derivative, right? So this is also the derivative of the derivative, dy dt. Okay?
Sorry, but do the 3 dashes mean anything?
Yeah, so when I put 3 dashes on the board for an equal sign, okay, what that means is the same as. Okay, so it means equals by definition, which is a different statement than like this. V equals minus 9.81t means these two numbers are the same. Okay, when I put a triple equal sign, it's meant to emphasize that by definition, this is what this is. Okay, so it's just for emphasis. Okay, so by definition, right, change in velocity over change in time as the change in time approaches 0, that's what we mean by the derivative, by definition. But v itself is a derivative. It's dy dt. So acceleration apparently is the derivative of the position. Okay, or I can write this as the acceleration is the derivative 2 times. Here's the notation for that. It's called the second derivative, d2y dt squared. Okay, take a look at the way that notation looks. Okay, this is the second derivative. Okay, and so very purposely here, the 2 in the numerator is next to the d here. The 2 in the denominator is not by the d, it's next to the t. Okay, now this is notation. Notation is made up by humans, right? Can somebody give me an explanation for why we might want to use notation like this, d2y dt squared?
The D's cancel out then.
The d's cancel out.
D on top.
So the d cancels out. So it would be dy t squared?
Something along that line.
The
Because
d's
then you
cancel
have-
out.
Then you have y over t squared,
Okay.
and the y is your distance,
Yeah.
and then t is in seconds, so that's your unit.
Okay, so that's a way to think about it. Like the d itself doesn't carry the units, it's the derivative operator. And so, that's a great reason for why the 2 stays on the t, right? So keep in mind, change in velocity, velocity is what? Units. Meter per second, time is what? Second. So it's meters per second, so it's meters per second squared. Right? So I do get a second squared down here, so that's a way to remember it. I don't like the explanation because d is not a mathematical variable, right? It means the change. So canceling out the d, I was going to let you run with it, but I wouldn't think about it that way really. The way I like to think about it as dt, the quantity, right, is the change in time. Okay? So the time, units of seconds, is what's being squared. So we get the t on the out, the 2 on the outside of the t here. Up top, the d2, it means it's the derivative twice, right? And so 2 derivatives of y. Okay, but yeah, the units carry like this. It's a square on the t, it's still a first on the y, right? So it's meter per second squared. Okay, so that's the units we choose. It means take the derivative once and then take it again. So back to our problem. That means a of t, I could start with y and take the derivative and then do it again, but I already did that, right? This is the first derivative. So the second derivative means the derivative with respect to time of the velocity. minus 9.81 t. Who wants to help me out? How do I take the derivative of minus 9.81 t? All right, so he's saying this is a t to the first power, right? So when you look at the sheet, you've got a t to the n. So you can use that power rule, n times t to the n minus 1. Once you do this a few times, you start to realize with a polynomial, if I have t squared, then the derivative now is just going to be t, right? The 2 in front. It knocks the polynomial down one order every time, right? So if it's a fourth order polynomial, take the derivative, now I get a third order polynomial. Here, I start with a linear function, first order polynomial, then I get a 0th order polynomial, which is a constant. Okay, so essentially, 1 comes down, t to the 0, which is 1. What happens to the constant? It just sits there, right? So the answer is just minus 9.81. What are the units on that? That's meters per second squared. Okay, and this thing looks familiar as what? That is g, right? So in this case, a of t is, by definition, g, right? Minus 9.81 meters per second squared. And that had to be the case if my physical model was accurate, right? Because the problem we're talking about here is free fall. Okay, so long as I'm not worried about wind resistance, right, and drag, okay, then that's it, right? The acceleration and free fall is what we mean by g. Questions? First and second derivatives, velocity, acceleration. All right, so let's see if we can make this problem, same idea, free fall problem, a little bit more interesting. And what if we now treat this as a projectile? Okay, so let's now suppose that the ball is projected vertically. Okay, so projected vertically, that means up. Okay, with, I got to say how fast I'm going, with an initial velocity. And the initial velocity I'm going to use in this case, I'm going to say it's v naught. Remember, anytime I put a little 0, it just means initial. V naught is equal to, let's use this, 4.43 meters per second. So now I'm going to think about this dynamics problem. Right? This is t equals 0 right here. Okay, and this is y equals 0. And I'm going to measure y of t here. Okay, if this thing has an initial velocity v naught of 4.43. Okay, and so I'd like to know some things about this. Okay, so from an engineering standpoint, all right, what problem am I solving? All right, this thing, not a ball, it's going to have to do. All right, throw it up in the air. What kind of things might I be interested in as an engineer? Maximum height, right? If I'm doing this in a confined space, I got to worry about hitting the ceiling. Okay, got to worry about, am I getting into an air traffic issue? In fact, we've got a high altitude balloon team here, which this is a real issue. They send a balloon. We get a team of mechanical engineers and electrical engineers doing GPS and these kind of things. And these kids send up balloons 90,000, 100,000 feet. So you got to get the FAA involved and worry about that. Okay, and so in engineering, anytime things are being projected, concerned about maybe how high it goes. Hey, also might want to know if it's going to go up, then it's going to do what? It's going to come back down, in which case I might end up with another impact problem, and I might worry about impact and dynamics and is it going to break and all these kind of things. Okay, so some basic idea of the dynamics and can I predict any of these things is of interest. Hey, so here's the idea. Okay, I'm going to say that for this problem, okay, I know what the answer is. Okay, and so the answer in this case for the position is going to be this. 4.43 t. In fact, you can see where this initial velocity ends up in the answer. Okay, minus 4.905 t squared. Okay, now if you've had some high school physics, you might be able to recognize where this equation comes from. In fact, the basic ideas of definition of a derivative, position, velocity, acceleration. if you had high school physics and you used the kind of equations we used in day 1 of this class, vehicle braking, v equals v naught plus a times time, right? It's what we call a constant acceleration equation. So whether you're talking about free fall or any other situation where the acceleration is constant, all of those equations in the high school physics book, it's just a little bit of calculus. You drive them all. Okay? So this is a similar equation here that you would get for this problem because, again, this is the vertical plane, right? I'm sitting here with gravity acting down. Okay? And so if this is the answer overall for y of t, what questions might we want to know? Okay? Number 1, how high does this thing go? Okay? And, how long does it take to get there? So, question 1, right? What is the maximum height? Right? And also, how long does it take? To get there. This is the question. So, first of all, let's say that I plotted this function. Okay, because we already talked about quadratic equations, right? And I've got y of t over here in meters, and I've got t over here in seconds. Okay, and without even putting numbers on here, can somebody suggest for me what would be the shape of this curve? All right, now keep in mind, this is not a projectile in 2 dimensions, right? Where this is height and this is length. This is height, this is time. Right? So the motion is 1-dimensional, straight up and down, right? But the plot that I have is going to be on a 2-dimensional graph. Okay? And so take a look at the equation. What kind of function is that? Parabola. Somebody said what? It's an upside down parabola. So I can get a kind of a sense of what this thing's going to do. Parabolas, do they have any symmetry associated with them? All right, this thing goes up, comes back down, right? It's symmetric about what point? The vertex of the parabola. Okay, so to get an idea qualitatively what this thing's going to do, first of all, at time t equals 0, what's the height? 0. So I know it's going to start there. I know it's an upside down parabola. Okay, and so, if it ends over here, it's going to go up, it's going to come back down after some amount of time, then the vertex is going to be where in between those points? Right in the middle. Okay, so again, without any kind of numbers, you get a sense for what this thing's going to do. So it's a parabola, and it's going to go up, it's going to come back down. So we'll go up, going to hit a flat spot, going to come back down. Okay? So, on this curve, apparently this guy right here, okay, the y value that corresponds to the vertex here of this parabola, okay, where again, this is it, y of t, 4.43 t minus 4.905 t squared. Okay, this height right here is what we're looking for. This is the y max value. Okay, I want to know that height. Incidentally, where on this graph is the time that it takes to get there? It's this symmetry line, right? It's the place that corresponds to the vertex. So this point here, this is t. I'm going to call this t max. Okay, now take a look at the subscript here. T max is not the maximum amount of time. It's the time at which the maximum position occurs. Okay, it's just notation, but that's my t max. All right, so what I would propose, okay, is there's more than one way to answer this question. If I understand my quadratics, I understand my algebra, I could be like, yeah, well, I could figure out, the total distance here, understand that this is symmetric, cut it in half, evaluate the function. I don't even need calculus to answer this question. Okay? The reason we like calculus is there's a lot of problems that I can't do that with just by looking at the geometry. And even for problems like this, I would argue you could do this faster with a little bit of calculus than what you could do by understanding the algebra. So, help me out. using an idea from calculus, how can I find the location of this maximum value? Somebody that hasn't talked to me yet. Yes, go ahead.
When the velocity equals 0.
When the velocity is 0. Okay, so I love that answer, right? And so the key is this happens when, right, at the time that the velocity, okay, is 0. You know, what I love about that answer is that's a physical answer, right? That's not a mathematical answer. It's this recognition. If this is going up and it's coming back down, then initially the velocity is positive. At some point, the velocity becomes negative, and it's a smooth curve. So clearly, there has to be a point in between where the velocity equals what? 0. Okay, so velocity equals 0 does not mean there's no dynamics going on. Could mean that. This problem right here. This is a statics problem. The velocity is 0. There's no dynamics. This problem, the velocity is 0 at an instant in time. Okay? It just doesn't stay 0 because it's doing what? It's accelerating. Okay? So realize that. I can have 0 velocity, which means I'm literally not moving, but I'm only not moving for an instant in time. Okay? All right, so great. I like that. So what does that mean? You know, back, you gave the answer. Velocity equals 0 corresponds to what point on the curve here? It is the maximum. Okay, so now who can give me the mathematical interpretation of why that 0 velocity is this point here? Say again? Because the tangent line slope is 0, right? So isn't it true that any time t, if I draw a tangent line to the curve at any point, that the slope of this is dy dt, okay? At any time t. So if this is the t value, right at that point, that slope is the derivative, okay? Which is, in dynamics, right, by definition, triple equals, that's velocity. Okay, so the statement that the flat spot up top has a tangent line that looks how? Horizontal, right? So the point is, right at the top, I know that dy dt, which is v of t, is equal to 0. Okay, so again, in engineering, right, we want to use concepts of calculus because we can find flat spots. Flat spots on curves that have no slope are also design points of interest to us, right? In this case, a design point where there's no velocity, it means I'm at the top and I'm turning around and going the other way. Great. So, what's the plan? If y of t is that function, okay, then apparently I'm going to need v of t equal to dy dt, right? I need to take the derivative. And to find the time, I'm going to do what with this? I'm going to set it equal to 0, right? So when I want to find a maximum value, step number 1 is let's take a derivative. Step number 2 is let's set it equal to 0. Questions on that? All right, so let's move forward with that. So in this case, v of t is the derivative with respect to time of the function I've got. 4.43t minus 4.905 t squared. So a little more complicated than the derivative we did previously, but not a whole lot. How many terms do I have here? I got 2 terms, so I can do the derivative 1 term at a time, right? So as I promised, as we move forward in this class, I'm going to quickly get to the way I would do one of these myself, all right, and try and cut down on the ink. So let's see if we can do this. First term. Who could tell me the derivative of the first term? All right, so this is a constant times t to the first, right? Take the derivative, says it's the constant stays. The 1 comes down, t to the 0. So I'm back to just the constant. So the first term, 4.43. Second term, So the 2 comes down. I got a constant out front, so I can say minus 4.905. I'll put this intermediate step, times the derivative of t squared, which is? The 2 comes down times t to the first. So this derivative is 2t. Okay, so again, 2 terms. T to the first just becomes the number 1. The constant stays out front. 4.905 and the negative stays out front. I take the derivative of t squared. I get 2 times t. Okay, and so apparently at any time, the velocity is equal to, right, 4.43 minus 9.81 times t. So a couple things to note. Y of t is what kind of function? It's position, but mathematically. It's a polynomial, more specific. It's quadratic polynomial. So y of t over here is quadratic. That's what I started with. Whenever I start with a quadratic, when I take a derivative, I end up with what kind of function? I end up with a linear function. So this guy now is linear. Okay, incidentally, if I take a derivative again, what kind of function will I have? A constant, a horizontal line. A derivative again will give me what physical quantity? This is velocity. I take the derivative again, I'll get acceleration. You can see what that's going to be, right? This term will be 0. This term, the constant will stay out front. This is still free fall. Right? This is interesting, right? In fact, the unbalanced forces acting on this problem that does this, okay, are exactly the same as the unbalanced forces acting here. It's just the weight. Okay, the only thing different is the initial conditions that I start the dynamics. Right? I start the dynamics in this case by throwing it up in the air. In the other case, I start the dynamics by simply letting it go. Okay, it's a general result in dynamics. The physical behavior you observe is extremely controlled by the initial conditions that happen. Right? 2 problems with the same unbalanced forces look like they're doing different things. Okay? But in fact, sensitivity to initial conditions is a big issue in dynamics in general. All right? All right, so that's linear. So, is that the answer? Do I have the maximum height now? No. Okay, so I got to keep going. So I got velocity at any point in time. How do I get the maximum height?
Set that equal to 0.
So if I set this equal to 0, okay. Okay, so set v of t equal to 0 to find, finish what you said, it's the t max, right? All right, so the value of t at which the velocity is 0 is what I'm going to be able to solve for here. Okay, so let's try that. So v of t, I just solved for it. It's 4.43 minus 9.81 t. That's equal to 0. Solving for this will give me exactly one value of time where this is true. Somebody crank this out for me. T is going to be what? 4.43 divided by 9.81, right? And that is what? 2.21? 0.45? Upside down. 0.45 what? How many? Is that it? 2 digits? 2 digits? 452? That's interesting. 0.452. Is that the answer to all dynamics problems, 0.452? Because I'm pretty sure that we did a different dynamics problem over here, right? And the accurate measurements we had, right, told us the answer was 0.452 seconds. Now we fire this thing up in the air, and it takes 0.452 seconds. It's odd. All right, let's see if we can figure that one out. Is that it? Is that the maximum height? Yeah, so this guy is actually, right, that's the T max. T max is equal to 0.452. That's this point indicated on the curve right here. So in order to find the value of the function at that point, what do I do with this number? I got to evaluate the function at that time. Okay, this is the number one mistake that introductory calculus students make, by the way. They do these max-min problems, they set something equal to 0, they get an answer and box it, and they think the problem's over. Okay? The question is, what's the maximum height? I need to know the time it occurs in order to get that, but once I have this time, I got to plug it back in. Okay, so finally, y max is equal to y evaluated at 0.452. So this is not y multiplied by, it's y evaluated at that. So let's plug the number in. Y is 4.43t minus 4.905t squared. 4.43 times t, 0.452, right, minus 4.905 times t squared, 0.452 squared. How high does this thing go? 1 meter. Is this the answer to all dynamics problems? Y max is equal to 1.0 meters. What the heck's going on there?
Ask a question.
Yeah. Go ahead.
All the acceleration forces on Earth are relatively constant. If you do a problem, say, for Mars, gravitational forces, you're going to get a different answer.
Okay. So for all dynamics problems on Earth,
Well,
is the answer y equals 1.0?
all of them using gravity.
Oh, it is?
No. It just depends on.
So like the ceiling here, is that more or less than 1.0 here? Probably more, huh? So apparently I can get up there. I'm still on Earth.
Depends on your initial velocity.
It depends on your initial velocity. Okay. So if my initial velocity is 0, the answer is 1.0. And if my initial velocity is 4.43, the answer is also 1.0. Is there another initial velocity that the answer would be 1.0? Who can tell me the relationship between this problem with 4.43 and this problem that takes 0.452 seconds to hit the ground? The starting point? So the starting point for either one could be the same, right? Whatever I call 0. So if my hip is the starting point, 1.0 meter in this case, right? And then here, this could be the same starting point. But I could also start it here with that same speed. So relative to here, it would still go how high? 1 meter. So you're getting warm. It's not the starting point. What is it? By the way, you were pretty warm, just not quite there. Go ahead.
In the last one, you find the final velocity was 4.3.
Was not the impact speed in this problem 4.43? So come on over here now. Here's the problem where y is 0 and I'm on the way up. If I come back over to here and start the problem over, y of t, how high am I?
1 meter.
1 meter, right? I'm still in free fall. What's my initial velocity? 0. Isn't the second half of this problem the entire first problem? So isn't this a parabola that is symmetric? So that means isn't the slope right here the same as the slope right there? What's the value of that slope? 4.43. Right? So that's it. So the reason why you get the same answer is because I chose the initial velocity to be the same as the impact velocity for the other problem, right? And it's the other half of the parabola. Okay, so the moral of the story is the answer to all dynamics problems is not necessarily 1.0, okay? And 0.452 depends on the initial conditions. All right, questions on that? Let me generalize this a little further, and then we'll do some more dynamics type applications. Hey, when I go through all this effort to find a max or a min value, you know, for this problem, it's pretty obvious that when I find a flat spot, it's a maximum value, right? Because I'm looking at it and I'm saying, well, there's only one flat spot. And I know what a parabola does, goes up, comes back down. And so whatever the flat spot is, that's the answer. Hey, but in general, I might have functions that are more complicated, that when I initially try and find a flat spot, I don't even have a picture of the function. Right? Or maybe I have the picture and I want to know what to look for. Okay? And so you can call this maybe an aside, but you'll use this result here. You know, what if you have functions that have flat spots that could be maxes or min values? You know, I could have a polynomial like that. What kind of polynomial has two humps? Is a sine a polynomial? Cubic polynomial in general can have two humps. Okay, great. And so these humps aren't exactly the same, right? Because look over here, right? Here's a flat spot, right? If this is y of t and this is t, right? Then at this flat spot here, I know I got dy dt is 0 there. But I also got a flat spot here, right? And so, you know, don't I also have dy dt equals 0 there? Okay, and so, you know, now is this a free fall problem? No. Free falling projectiles don't change and start going back up again. Okay, could be some kind of hovercraft, projectile motion, up and down, whatever. But, you know, what if this is like power consumption in a laptop or something, right? And I want to make sure I optimize this so the battery lasts longer. I'm pretty sure I don't want it designed to be this one. I actually want this one. All right? And so I got to have some idea of, am I going to design now for a maximum or am I going to design for a minimum value? And so who wants to help me out? We got a whole bunch of people claim they've had calculus before. It's got to be a strategy here from calculus to figure out, how do you know if I got a max or a min? Good.
I mean, you're going to find two values for t, and then you plug them both into the original. Or when you set the first derivative equal to 0, you're going to get two values because it's going to be some function squared.
All right, so in a problem like this, what are you saying right away? Is, hey, this could be cubic. If I take a derivative, I'll get a quadratic. If I set that equal to 0, I'll get two answers.
Yeah.
So definitely it's clear that I can find 2 points. Okay? Yes, I'll find 2 points.
And then you plug them two values into the original equation, which whenever is bigger or smaller is the max or min relatively.
Okay, so you could come back in if you know that this is a cubic, right? And you know that there's only 2 answers. Okay? Then you could say, well, I mean, that's it. If I just plain evaluate the numbers, whatever one's bigger is the max. That will absolutely work as long as you know this is a cubic and there's just the 2 answers. What if you got some problem where you don't even have an analytical solution? You're trying to find the derivative like numerically. Okay, and so you find some region in design space where it's flat. Is there any way to tell whether that flat part is a part that's the biggest local value, you know, it's going to turn around and go down? Or could it be the smallest local value where it's going to turn around and come back up?
Sign changes.
Sign change. So what would that, what's a sign change of what?
Yeah, when it, like, if it has a positive value, then you're like going up, and then if it turns to a negative value, then it's going down.
All right, so she's talking about changing from positive to negative. What would be changing from positive to negative if I was near a maximum? The slope, right? So to the left of the point, I can evaluate the first derivative. And the way I have it shown here, this would be what? A positive or negative slope? That's a positive slope, right? The whole argument here is I know this point has 0 slope. So we're trying to see, is the slope going from positive to 0 to negative? So you could find the points, and then you could scooch to either side of that, and you could check the slopes for a sign change. It's kind of the brute force method of doing this. They call this the first derivative test in calculus. But honestly, unless the second derivative is a hard thing to compute, okay, I would rather just cut the chase and do the second derivative. And in fact, in dynamics type problems, you know, I want the second derivative anyway. All right? Second derivative is what quantity? Acceleration. Why in dynamics do I care what the acceleration is? Right, if I'm worried about the maximum height, do I need acceleration for that? I mean, it's part of the physics, but I mean, I just need to know the height, right? I need the y value. Why do I care about the acceleration value? Beck.
That's when it's changing from positive to negative, then that's a 0 point.
It's a 0 point of what, the acceleration?
It's either a maximum or a minimum.
Okay. So, why else? In engineering in general, why do we care about acceleration? Like, how's this? Would you buy a sports car that when you stepped on the gas, you get 15 G's of acceleration? You would buy that sports car? What could be a problem with that sports car? It'd kill you. All right, so here's the thing. This is interesting. We got biomedical engineers in the room, right? Is acceleration the thing that actually damages the human body? What damages anything?
What change in the acceleration?
Force. More importantly, force distributed over area, right? Your femur can take a lot more force, right, than your phalanges, okay? So bottom line is, it depends how big it is, et cetera, but force acting over a certain area, that's called stress. That's what breaks things, right? Whether or not this thing smashes when it hits the ground, it's the impact force that controls that. So I got position, I got velocity, I got acceleration. Which one of those three things corresponds to force? Acceleration, right? Many people have had physics. F equals m times what? A. Okay? A matters. Acceleration's a big thing that matters. So if acceleration matters, then I got to take a second derivative anyway. And if I need a second derivative, then I might want to use that concept here. Okay, so who can recall? How do you use a second derivative to say if I've got a max or a min?
When the second derivative is equal to 0, it's a change in concavity.
Okay, what's concavity mean?
The dome of the curve.
The dome of the curve. Like, okay, so this would be called concave what? Concave down. Okay, so you're right. There's a change in concavity when the second derivative is 0. That's called an inflection point, right? Like when I go like from here to here, the inflection point is like, right there where I'm neither concave up nor concave down. This inflection point is not really helping me with a max or a min here, right? You're on the right track. What can I say about the second derivative when I'm near a maximum? The second derivative is the derivative of the first derivative, yes? So the second derivative is the way that the slope changes, okay? So take a look at the slope here. The pen is the slope, right? Slope is positive. Slope is 0. Slope is negative. How is the slope changing? In a positive way or a negative way? Yeah. Two derivatives with respect to time here, less than 0, right? At a maximum, concave down means second derivative is negative. Okay, so this is concave down. That's at a maximum, right? At a max. Over here at a min, again, take a look at what the slope does, right? As I move to the right in time, I start with a negative slope, then a 0 slope, then a positive slope. So my slope is changing in what? A positive or a negative way? Positive way. It starts negative, it becomes 0, now it becomes positive. The slope is increasing algebraically. That is a statement, right, that two derivatives of y with respect to time, okay, is greater than 0, okay, and this is what we call concave up. Okay, and this corresponds to a minimum value. Okay, so one quick way to think about it, it's sort of the opposite sign-wise, right? A maximum is a negative second derivative. a minimum is a positive second derivative. Unless the function starts right here and ends right there. And if I want to know the real max and min, which points are these? These are the endpoints. Okay, so one pitfall of calculus in all max-min problems, but definitely in engineering design. You got a design space, your worst case could be the endpoint, the end of the space. Right? The end of the space might not be a flat spot. Right? So when you want to know the overall design, what's the worst case, what's the best case, you got to find all the flat spots, you got to find the endpoints, and then you got to find the points where, what if my function does something weird like this? What's the value of the derivative right there? This is an undefined derivative, right? Because I got one value just to the left, I got a completely different slope just to the right. The derivative doesn't exist at that point. So in general, in design, I'm going to use derivatives. I want flat spots, right? I want points that aren't defined. And then I got to look at my design space, and I got to check the endpoints. Okay, but that's really all the possible points. Flat spots, undefined points, endpoints. Then you're done, and you're sure that you don't have anything else. Okay, I actually like the very first answer. If you know what the function is, and it's a cubic, and I only have two values, just compare the numbers. Okay, you don't even use second derivative. So if you know about the function, you can answer the question that way as well. Good. Are we good? Derivatives. You know, that is the entire learning objective of derivatives. Okay, so for the whole rest of today and all next week and a week after that, all we're going to do is apply this stuff in context that much of which you haven't seen. Okay, the first one will be some context that I think you have seen if you've had some dynamics. And not everybody's taken physics in high school, right? So if you took physics in high school, the ideas of position, velocity, acceleration, pretty comfortable with those. Okay, and so what I want to do just briefly, okay, is just kind of sum up, what do we have? Okay, and so in the field of dynamics, what we've shown from this kind of first set of problems, okay, is that in general, okay, for position, velocity, okay, and acceleration, these are the three things I care about in dynamics problems. Okay, position and velocity, because they really describe the motion. What's happening, where am I at any point in time? Acceleration, because that corresponds to the force, right? It also corresponds to if I'm trying to control what an object does, like attach a little jetpack to my hovercraft and make it do things. I make it do things by applying to it the force, right? So the acceleration is actually what, as the engineer, I can be controlling that, right? Or I can be directly measuring that. When you go to measure dynamics, you use things called accelerometers. Right? It's a little electrical device that it's a material science concept. When that device is subject to force, and it's got force because it's got acceleration, then the material behaves in a certain way, right? And you get an electrical signal from that material. Okay, so position, velocity, and acceleration, okay, is essentially the idea. I can think about this as kind of a hierarchy of three things. Okay, I could think about maybe a problem of a vehicle. Okay, and this vehicle at any point in time, okay, is located x of t away from the starting point. Okay, and so I can think about, how does the position x of t in meters change in time? So maybe this thing starts off, right, at 0 position, and it starts at rest. Okay, well that means the slope of the position is 0. Okay, so maybe it starts to speed up over time. Right? And then maybe it cruises for a little while, and then maybe it bends back off again and ends up with a velocity at 0 at some endpoint. Hey, well, the velocity of that same thing, okay, is the rate of change, right? So the velocity is v of t is dx dt, right? And that is the slope of x of t. Okay, so the same problem here, if I come now underneath that and say, well, what would the velocity now, v of t, in meters per second look like, okay, as a function of time in seconds? Okay, then you would look at this function and say, well, in general, this thing is curved here, so if it's polynomial, it would be like a quadratic. Then it looks to be sort of a straight line for a while, and then maybe another parabola back down. So you keep in mind that the velocity is the slope, right? One less order of polynomial than this. So even graphically looking at that, the initial slope of this curve is what? 0. So apparently I'm starting here, right? And you know, what is the slope doing? It's 0, and then it's increasing some. If this was quadratic, then the slope would be increasing linearly, right? Derivative of quadratic is a line. So, well, if that's true, then this is probably just a line that goes to here. Okay, and then over here, if I have a constant slope, say between this point and this point, then the velocity graph would be what kind of function? Yeah, I'd be cruising, right? This is what cruising looks like on a velocity graph. And then finally, maybe this is now an upside down parabola where I start with a certain slope and I decrease. If this is a parabola, then the decrease would be linear and it would come back down to 0, you know, like that. Okay, so graphical relationships between position, velocity, and then ultimately acceleration are a lot of the things we're interested in, right? In fact, if I'm controlling this vehicle, right, and I want to make it go back and forth, what am I literally doing? Raise your hand if you get a driver's license. All right. Huh? Temps count. Okay? So, what am I literally doing to make this thing go back and forth? I'm doing what? Yeah, but what am I doing? So I'm sitting in the car and I want to go. What do? I press the what? Oh, I don't press the velocirator or the position increaser. I press the accelerator, okay? Because when I press the accelerator, it causes the engine to do stuff, right? If you want to be a mechanical engineer, right? Which effectively applies what to the car? Force. So again, you control force, which causes acceleration, which causes the dynamics, right? So how would I control force that caused me to do this? Start from rest, start speeding up, coast for a while, put on the brakes. How would I do this? Well, I need the acceleration here, which I control, right? Which is a of t is dv dt, right? Okay, and so this is the same as 2 derivatives y with respect to t. Sorry, we're using an x. 2 derivatives x with respect to t for the position. Okay, and so this guy now is another slope, right? It's the slope of v of t. By the way, if a is the second derivative, what does a tell you about x? The second derivative of x graphically tells me what about the curve? It's the rate of change of the rate of change, but when I look at this plot, the second derivative of this plot tells me what geometric characteristic of the region. So like, what's the difference between this piece and this piece? Yeah, it's the concavity, right? So it's the slope of v of t, and I'll put in parentheses, it's the concavity. It's the concavity of x of t. Okay, so in fact, I can get information right about x, right, straight from a, or vice versa. If I see the position, I can know what the acceleration might have to be. This part over here is what? Concave up or down? This is concave up. This one's concave down, right? Or I can look just at the slope. So what would an acceleration look like that would correspond to this. Well, acceleration is the slope of v. Is the acceleration always a positive number for this problem? Do I get places where the slope of v is negative? Yeah, right. So don't I have positive slope here, 0 slope in the middle, and negative slope over here? So I've got all that going on. So really acceleration apparently, to have this going on, right, is an a of t in meters per second squared that for the first part is just a constant value, right? Because the derivative of a line is a constant, right? One less order polynomial. And then over here, clearly, dv dt is 0, right? Horizontal line. So the acceleration apparently is 0 between those points. Okay, and then at the very end, looks to me like the slope is negative. Again, this is a line. Slope of a line is a constant value, right? It's a negative slope over here. So a position like this, okay, this is your mom pulling the minivan into the garage, right? Slam on the gas, going up the driveway, coast in there, slam on the brakes before you hit the living room wall, okay? That's what the plot looks like. Okay, and this is time over here in seconds. All right, so this is the general relationship, right, between position, velocity, acceleration, the idea that I can use calculus concepts. Right? I don't have any numbers here. Calculus concepts to understand the type of function, the behavior of the function, what it does. Okay, and so, this function is piecewise continuous. It's not even a smooth function. It gives me a function here which is at least continuous, okay, but it's got corners on it. And this one actually gives me a smooth value of the position, right? The position has to be smooth, right? If the position's not a smooth function, then what's happening to you? Severe bodily injury, right, at some point? I mean, you can't displace instantly without what type of acceleration? Negative? This acceleration is negative right here, right? Instantaneous displacement requires how much force? A lot. Yeah, right. Instantaneous displacement. It's a teleport, right? I mean, infinite force, theoretically, right, to move you like that. So, I mean, the point is severe bodily injury, okay? So you can't have that. All right, so knowing all this, let's get a little bit of practice. Start with some particle motion. Okay, so let's say you might even do some of these problems kind of just like this in introductory physics. Okay, let's take a look at the motion of a particle, okay, in the horizontal plane. This is x of t right here. Okay, and we'll take a look at certain values of the position. Okay, and what I would like to find, okay, is the following. I want the position, okay, I want the velocity, and I want the acceleration at a specific point in time. Okay, this is at t is equal to 0.5 seconds, okay, for several different values of x of t. Okay, so first example, let's say that x of t is a sine function, the sine of 2 pi t, okay, and that's meters. Okay, so we've already talked about sinusoids, but in general, if I have a function sine of 2 pi t, what can you tell me about that position? If this thing was really going to have a position that was a sine function, yeah, it would probably be in a horizontal plane on wheels attached to the wall with what? With a spring, okay? And I could pull it and let it go and it would do this, right? Because the spring stretches, pulls it back this way, it passes equilibrium, it compresses the spring, it gets pushed back the other way, causes an oscillating motion, right? So that would be that, sine 2 pi t. Great, so this is derivatives practice for those that haven't had much calculus. Okay, and let's go ahead and do this. Position, velocity, acceleration at half a second. Okay, so what do I need? Velocity, v of t. X of t is a sine, 2 pi t. Help me out. V of t, dx dt is the derivative, right, of the sine of 2 pi t. And so we got the sheet over here, right? Those of you that haven't had calculus before, all right, these are the functions we want you to be able to do. Sine omega t, cosine omega t, e to the st, t to the n, right? And that's pretty much it. Help me out. What's the derivative of the sine function? It's the cosine function. What about the frequency over here? What happens to that? Goes outside. Okay, so what happens here is v of t is, according to the sheet, this is sine omega t. Omega comes out times the cosine omega t. So the omega is the 2 pi, and I get the cosine of 2 pi t. What are the units on that? Yeah, this guy is going to be meters per second, right, if this one starts in meters. Great. I want the acceleration also. Acceleration is dv dt. So now I got to take the derivative of the derivative I already took, of 2 pi times the cosine of 2 pi t. Help me out. What do I do with the 2 pi out in front?
Square.
This guy. Well, you said square it, okay, but it's a two-step process, right? The constant stays out front, and the reason it gets squared is because this guy does what? Comes out front also. So it's really two steps, right? A of t is the 2 pi is out front. Now we'll multiply that by this derivative. The derivative of the cosine omega t is what? Negative sine omega t. The omega comes out front. So the omega comes out. I got a negative 2 pi. Derivative of cosine is sine. Sine of 2 pi t. Again, if you have never had calculus, okay, a lot of students in here rattle that off. It's because they've had calculus. This is just a subset of derivatives we want you to know in here, right? So it's one of these things, you'll just memorize what's in the table over here for how to take these particular small number of derivatives, okay? So that's it. And so in this case, I end up with this squared, right? So a of t is now equal to minus 4 pi squared times the sine of 2 pi t. What are the units on that guy? Meters per second squared. All right, so started with position. I got velocity by taking one derivative. I got acceleration by taking another derivative. But the question was, what are the position, velocity, and acceleration at one specific point in time? All right, so let's evaluate these guys at the required time. T equals 0.5 seconds. So at t equals 0.5 seconds, what do I do with the number 0.5? I plug it in, right? So the point is, when I take these derivatives, I have the answer at every single point in time. If I want a number, I put the point in time in there and see what I get. Okay? So in this case, x of t, sine 2 pi t, plug it in there. X evaluated, not multiplied, right? Evaluated at 0.5 is equal to the sine, right, of 2 pi times 0.5. What's that equal to? 2 pi? I got one vote for 0. Can I get some corroboration here? So this is the sine of pi, right? Sine of pi, 0. It's on the axis. Okay, so I get x is equal to 0 meters. Great. So it's at the starting point. Okay. What about v? V of 0.5 is, what do we have? 2 pi times the cosine 2 pi t. 2 pi times the cosine of 2 pi times 0.5. What's the cosine of pi? 2 times 0.5 is 1, right? So this is the cosine of pi. Pi over 2. What is it? 1 over root 2, did somebody say that? Cosine of pi is how much? -1, right? So we are over here, right? 1, 2, 3, 4 quadrants. Over here, this is pi, okay? And so the cosine over here, I'm right on the x-axis, okay? So I'm at -1. So apparently then, v is equal to how much? -2 pi. -2 pi meters per second. All right, so apparently I'm at the starting point. I'm moving which way? To the right or to the left? Moving to the left, okay? And what's happening to my speed? I need the acceleration at 0.5. Okay, so according to that, it's -4 pi squared times the sine again, right, of 2 pi times 0.5. What's the sine of pi? 0. Okay. A equals 0 meters per second squared. Okay. So, interesting. I'm at the starting point. I'm moving. I got no acceleration. It's going to move forever that way, do you think? I'm at the starting point. I'm moving. I got no acceleration. Isn't that, you know, an object in motion stays in motion? Unless what? Unless acted upon by an unbalanced force. How do you get sinusoidal behavior of a mass? Well, probably need to have a spring over here, right? So what we're talking about is the point where I've reached equilibrium, and now I'm going negative, and I'm compressing the spring. So right at this instant in time, yeah, I don't have any acceleration, but any infinitesimal time later, I'm going to have acceleration going the other way. Okay, and so yeah, it's moving left, it's passing the 0 point, it's not yet accelerating because there's no net force, but the second I have a net force, it'll accelerate. Okay, so that's how you would get that. Questions? Position, velocity, acceleration. Okay, so let's stick another one in there. What if I have a polynomial in here now? Okay, so let's say, for example, let's say x of t is equal to 3t cubed minus 4t squared plus 2t plus 6. Okay. What do you think? Okay, so I want to evaluate position, velocity, and acceleration all at this time. So I need v of t, which is dx dt, which is the derivative with respect to time of that whole guy. 3t cubed minus 4t squared plus 2t plus 6. I got how many terms there? I got 4 terms. All right, do I care whether I've got 1 term, 2 term, 3 term, 4 term, 5 term? Now, I do 1 term at a time, right? Derivative of the sum is the sum of the derivatives. Great. So 1 term at a time. Each one of these, are these on the sheet? These are t to the n powers, right? The only difference is they got constants in front. What do I do with the constants in front? They just sit there. Okay, so each of these is just a t to the n. I do the constants in front. So the v of t, all right, so walk me through. So the 3 stays out front. Okay, I'll go ahead and put the answer. So this is going to be 3t squared here. Minus 4. Yeah, derivative of t squared is 2t plus. Yep. Derivative of t is 1. Yep. And what's the derivative of 6? 0. Okay? So that's it. Now, again, I don't even need to see this level of intermediate step, right? If you can just look at this and multiply the constant, I'm fine with that. So it's 9t squared minus 8t plus 2, and I can box this meters per second. Okay, so this is v of t. Any questions on how I did that derivative? It's 1 term at a time, power rule. Okay. Acceleration. All right, the beauty of polynomials in calculus is the further you go, the easier it gets. All right, I knocked it down one level every time. So a of t is now dv dt. I need the derivative with respect to time of this guy, 9t squared minus 8t plus 2. Incidentally, I started with a cubic, right? So when I take the derivative, I get what kind of function? Quadratic. Now I've got a quadratic, I'm doing a derivative again, what am I going to get? A line. If I kept another derivative, I'd get a constant, right? Next one down from a line, and then one more time would give me 0. Okay, so I'm stopping at acceleration. Okay, and so what do I get here? So a of t, okay, is what?
9, 18t minus
Yeah, let's do this in one fell swoop. The 9 stays times 2t gives me what? 18t. How about the 8t? Minus 8t to the first. How about the 2? Yeah, 0. Okay, 18t minus 8 meters per second squared. That's the acceleration. Okay, so again, if the question is evaluate these at 0.5 seconds, I'm not done yet. I got to go back to each function, see what the answer is right at that point in time. So at t equals 0.5, I got to take each one of these, plug in the number. So these, unless you're good with decimals and cubes and such, you might want to pull a calculator out, see what we get. X evaluated at 0.5 is 3 times 0.5 cubed, right? So 0.5 cubed minus 4t squared, 4 times 0.5 squared, plus 2t plus 2 times 0.5 plus 6. Somebody crank that out for me. What's x? 6.375. That's what I got. 375 meters. Okay. Let's see. How about velocity? V evaluated at 0.5. Okay, so now, again, it gets easier as I go. V is this guy. It's a quadratic. So V of 0.5 is 9 times 0.5 squared minus 8 times 0.5 plus 2. Okay, what do you think? So it's negative 4 plus 2 minus 2, and then what? 0.5 squared? 0.25? 9/4? What do we get? 0.25 meters per second. That's V. Okay, and then finally, the easiest one is last. A of t is 18t minus 8. A of 0.5, right? 18 times t, 0.5 minus 8. 9 minus 8 is how much? Sorry. Yeah. 9 minus 8? 1.0. A equals 1.0 meters per second squared. All right, and then there's one more in that example. It's a cosine minus a polynomial, one term at a time, okay? So we're going to spill over dynamics a little into next week. Next week on a schedule says circuits. I don't need 2 80-minute lectures to do the circuits, okay? So we'll finish up dynamics on Tuesday, and we will get through the circuits probably by the end of the week. I am posting homework when I get back to my office, so like always, homework will be due on this material end of next week on Friday. Okay, so this week's homework will be all dynamics, the derivatives and dynamics. Have a good one.